In this video on Bayes' theorem, in this video we'll look at the definition of Bayes' theorem, some interesting psychological research that relates to the intuition of how people often perceive conditional probability, and also an example of using Bayes' theorem in a concrete example. Okay, so Bayes' theorem. Bayes' theorem is best described by the formula that you'll see at the top here, where the probability of A conditioning on B is equal to the probability of B conditioning on A times the probability of A divided by the probability of B. And if we focus on just understanding this first, when we're dealing with the probability of A conditioning on B, we're trying to work out how likely it is for A to happen given an extra piece of information that is contained in B. And in the real world, this is stuff that we do as humans all of the time. We're often working out how likely something is to happen, and we're making our decision of how likely it is to happen, or our insight into how likely something is to happen, based on information that we have. And we're using this concept of conditional probability to do so. And Bayes' theorem is so useful because it provides us with a platform of actually establishing exactly what this conditional probability is. And whilst it might look confusing written down, these are often things that you can determine and evaluate and then plug them in together to work out exactly what this is. But yeah, it can be hard to understand what all this means, and I'll come back to it later. But first, let's just look at some intuition and big picture, simple stuff to get us thinking about Bayes' theorem and what it looks like in practice. And I want to look at some psychological research by Nobel Prize winning psychologist Daniel and Amos. I'll only say the first name with the last names there. And I saw a video explaining Bayes' theorem talk about this research, and I think that it's a really good way to understand intuitively what Bayes' theorem actually is. So first, let me pitch to you a question that they asked in the experiment. Steve is a very shy and withdrawn, invariably helpful, but with very little interest in people or in the real world of reality. And so I'm just describing to you what this person's type is. A meek and tidy soul, he has a need for order and structure and a passion for detail. So given this description of what Steve is like as a person, do you think that Steve is more likely to be a librarian or a farmer? And why, I guess, is the question. So a lot of people who were asked this question in the experiment, they gave an answer that is interesting. I guess I'll give you a second or two to process what you would say for this. Based on this description, do you think he's more likely to be a librarian or a farmer? And in order to have a informed decision, you need to use Bayes' theorem correctly, which is the one that we're looking at in this video. So what do you reckon? Well, most people say that he's more likely to be a librarian because when we think about librarians and farmers, this description here is just so accurate to what many librarians that we know and can think of are like. They're usually helpful people, but they might be shy. They're very tidy, need for order and structure, passion for detail. Like, this is very much a description of a librarian. I think farmers can be like that, but maybe they're less like this, which says they have no interest in people or in the real world. I feel like you need a lot of interest in the real world to run a farm well. But yeah, based on this description, we think in our head that they're more likely to be a librarian than a farmer because this description is better suited to a librarian or a farmer. But to actually know if it's true that they're more likely to be a librarian, we need to think about how many people are librarians versus farmers, because this description might actually describe a librarian compared to a farmer. But if there's just so many more people that are farmers in the world, then the complete Bayesian probability of someone being a librarian given this description is still going to be relatively low. So to understand what that looks like, let's take a look at this visualization. So let's say these are all the possibilities of people that are librarian or farmer. And then in the whole world, there's just a lot more farmers than librarians. So you can see this represented as a greater area shaded for farmers. And then we can apply the evidence to this description and see that most librarians fit the description. So not all of them, there's some that has been removed, but most of the librarians in this column here are these tidy, shy, withdrawn people who have a passion for detail and order. And there are some farmers that also fit this description, but relatively speaking, the percentage of farmers that fit this description is much less. And you can see that this percentage is so much smaller for farmers, but because the total area of farmers to begin with is so much more, there's still just so many more people that match this description that are farmers. And when we work out the probability that they're a librarian given this evidence, we're basically saying we know that they have this evidence applied to them. So all these people left in the shaded on the right here are people that match this evidence. And the probability that they're a librarian given this means that if we were to randomly pick a spot in this area, what's the chance we would land in the orange zone as opposed to the green zone? And that's just the area of orange plus divided by the area of the total area of people that fit the evidence. And yeah, that's going to be smaller than if you were to have farmer as your answer, because there's more farmers that match this evidence than librarians. And essentially, this is an application of Bayes' theorem. So in this case, the probability that they are a librarian given the evidence is the number of librarians that match this evidence divided by the number of people who just match this evidence at all. And in this case, it is equal to this area here. And yeah, hopefully this is an example intuitively of how we can use Bayesian probability and updating to understand conditional probability and how likely something is to be true given the evidence. And if you look back to the formula, a really key component in any representation of this same concept is that the probability is equal to something on top. I think probably made this one is the quickest one to look at in terms of conditional probability. You're looking at all of the ways that A and B exist together. This is the intersect sign, the intersection of A and B, and then contextualizing them both taking place in the bigger picture of B. So if I'm focusing on how likely it is for A to be true given B, I'm looking at all of the circumstances where A and B are both true together, and then just seeing how often B happens to know that once I know B is happening, within that conditional mindset, how likely is it for A to be true as well? Another way you can think about it is if I condition on knowing B is true, everything else is no longer relevant. I can discard these events and not cast any thinking towards them. And then just look at within all of this new world where only B exists, how often does A happen as well? So how often does A happen in the world of B? And then how big is this world of B? And that will give us this conditional probability. And these are other ways of representing the same formula, just using other probability rules alongside it. So law of total probability is used at the bottom here because the probability of B happening is the sum of conditional probability of B to another event that partitions the whole space, but that's due to the law of total probability. And the probability of A intersect B is equal to the probability of B given A times probability of A. Yeah. All right, so let's look at another psychological example, which I think is interesting because people also... Oh, I don't want to position you before. I'll just show you the example and then we'll talk about the example. Okay, Linda is 31 years old. She's single, she's outspoken, and she's very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more likely? A, Linda is a bank teller, or B, Linda is a bank teller and active in the feminist movement. So we've got this question for you. Hopefully your trust in these questions hasn't been betrayed from the first one. But the idea is that if we look at this description of Linda, we've got single, outspoken, bright, majored in philosophy, deeply concerned with issues of discrimination, social justice, participated in anti-nuclear demonstrations, so she's very proactive as a person. And if we think about these options here, B is looking quite appealing to us because someone who's active in the feminist movement seems to match this description above. It's resonating with us that when we see a person described in this way, that is the type of person we imagine would be active in the feminist movement. But is it true that it's more likely that Linda is a bank teller and active in the feminist movement? And the correct answer to this question is that it's more likely for A to be true, Linda is a bank teller. And the reason for this is not because it's unlikely she is a feminist, but because every feminist that's a bank teller is still just a bank teller. And then all of the bank tellers that aren't a feminist are included in this option A for being a bank teller. So we don't actually have any reason to pick B, because even if 90% of Lindas of this type who are bank tellers are also feminist, there's still less of them than 100% of bank tellers that are just a bank teller. Every single person who matches the description of B also matches the description of A, because part of the requirement of being a match to B is that they're a bank teller, and Linda is a bank teller already. So yeah, this is just another, I guess, psychological example, which I find interesting, that people in the experiment are more likely to pick B, demonstrating that Bayesian conditional probability can be hard and that people aren't always good at it in practice. All right, let's look at a concrete example now to finish off this video. So here's an example of using Bayesian probability in practice. Let's look at it step by step. Okay, so a blood test is 95% effective in determining a certain disease when the patient has it. However, 1% of people who don't have the disease receive a false positive. If 10% of the population has the disease, what is the probability a person has the disease given that they tested positive? So this is a Bayesian scenario. We're trying to work out the probability of an event happening, conditioning on the fact that we have a piece of information. And in this case, the piece of information that we have is that they've gotten a positive test. Perhaps you find this example particularly interesting in light of recent events over the last couple of years. So we want to start by just defining the events clearly. This is a good practice for these types of questions. So let A be the event that you have the disease, and let B be the event that you test positive. And what we're trying to figure out is what is the probability of A given B. And using our formula of Bayesian's rule, that is equal to the probability of B given A times the probability of A divided by the probability of B. So do we have all of these pieces of information in our scenario? Let's look. Well, the probability of B given A is the likelihood that you test positive given that you have the disease. And if we look back to the question, I think that tells us that quite directly. 95% effective in determining a certain disease when the patient has it. So this bit here is 95%. PA, probability that you have the disease. 1% of people, oh no, that's not useful. 10% of the population has it, there we go. So this here is 0.1 because 10% of the people have it. This is 0.95 because it's 95% effective. And then let B be the event that you test positive. This one is trickier. So walking in, how likely is just any person to test positive? Well, we can use the law of total probability here because the chance of testing positive is going to equal the sum of chances of having the disease and testing positive plus not having the disease and testing positive. There's two ways that you can test positive, either from having the disease or not. And the sum of those probabilities together will give us, using the law of total probability, the likelihood of someone just testing positive point blank. Okay, so if we expand it out here, the law of total probability is being put into practice down here. The chances of B occurring are the chances of B occurring conditioning on every option of A. So A and not A is people who have the disease and people who don't have the disease, and then multiplying it by the probability of A and the probability of not A. So look down here. We've agreed that this was 0.95 and 0.1. And then down here, someone who has the disease and tests positive, that will happen 95% of the time. And then just any random walking in to get tested is 0.1 probability of being someone who's sick if they're just a complete random. And then someone who doesn't have the disease only has a 1% chance. If we look back up here Yeah, they only have a 1% chance when they don't have the disease to have a false positive. So 90% of people don't have the disease, and each time they test, they have a 1% chance in testing positive. So adding these together gives us a chance that any person that you pick will randomly test positive. Okay, and plugging all of that into the formula gives us 0.913 as our answer at the end here for Bayes' theorem. All right, I hope you found that helpful, this video on Bayes' theorem, looking at the theorem itself and some psychological studies about people's ability to use Bayesian updating, and then a practical example of solving a question using Bayesian updating as well. All right, thanks for watching the video. I hope you found it helpful.